Ever look at your messy room and wonder, how did it get this bad? Well, congratulations. You've just had a run-in with one of the most fundamental concepts in the universe, entropy. But what is it, really? Is it just a scientific term for messiness? Stick around, because today we're unraveling the mystery of entropy, nature's ultimate driver of chaos, and trust me, it's way cooler than just a pile of laundry. Let's start with a simple thought experiment. Imagine you have a box. On one side, a bunch of hot, fast-moving gas particles, and on the other, cold, slow-moving ones. There's a divider in the middle. Now, what happens when you remove that divider? The particles don't stay separated, right? They mix. The hot particles share their energy with the cold ones until everything reaches a uniform temperature. You'd never expect them to spontaneously separate back into hot and cold sides. That irreversible mixing, that march towards uniformity, is entropy in action. This is all governed by the second law of thermodynamics, which basically states that the total entropy of an isolated system can only increase over time. It never decreases. Think of it as a one-way street for the universe. Time flows forward, and with it, entropy increases. This is often called the arrow of time. It's the reason why eggs don't unscramble themselves, why buildings crumble but don't spontaneously assemble, and why your coffee cools down but never heats up on its own. It's the universe's tendency to move from a state of order to disorder. But let's get a bit more precise. Disorder can be a misleading word. A better way to think about entropy is in terms of probability and the number of possible arrangements or microstates. Imagine you have 4 coins. How many ways can you get all heads? Only one. That's a low entropy state, very ordered and specific. Now, how many ways can you get to heads and to tails? 6 different ways. This is a high entropy state because there are many more possible arrangements that result in the same overall outcome. The universe, with its countless trillions of particles, is always moving towards the state with the most possible arrangements, simply because it's statistically the most likely. It's not some malevolent force pushing for messiness, it's just playing the odds. So, your room getting messy? It's not your fault, it's physics. There are vastly more ways for your books, clothes, and papers to be scattered around a high entropy state than for them to be perfectly arranged on shelves, a low entropy state. Left to chance, they will almost certainly end up in one of the many disordered states. To create order, to clean your room, you have to expend energy. This brings us to a crucial point. You can decrease entropy locally, like by cleaning your room or building a skyscraper. But you do so by increasing the total entropy of the universe somewhere else. The energy you use to clean releases heat into the environment. Your body metabolizes food, and the power plant that gives you electricity burns fuel. All of these processes increase the overall entropy of the cosmos. So, while you create a small pocket of order, the net result is always more total disorder. This concept extends to everything, including life itself. Living organisms are incredible examples of low entropy systems. We are highly organized, complex structures. So, how do we defy this cosmic trend toward chaos? Well, we don't. We are what the great physicist Erwin Schrödinger called entropy-sucking machines. We maintain our internal order by taking in energy from our surroundings like food and sunlight, and then we export a massive amount of entropy back into the environment in the form of heat and waste. A plant uses sunlight to build complex sugars from simple molecules, creating order. But in that process, the sun is burning through its fuel, a process that generates a colossal amount of entropy that far outweighs the small pocket of order created by the plant. Life doesn't break the second law, it masterfully exploits it. Now, let's zoom out to the biggest scale imaginable, the entire universe. Our universe began in an incredibly low entropy state at the Big Bang, a hot, dense, and remarkably uniform point. Since then, it has been expanding, cooling, and its entropy has been steadily increasing. Gravity pulled matter together to form stars and galaxies, which are pockets of order. But these stars are cosmic engines of entropy, fusing elements and radiating immense amounts of heat and light into the void. They create order locally while driving up the universal entropy score. This leads to a rather sobering prediction about the ultimate fate of the universe, a theory known as the heat death. If the universe continues to expand and entropy continues to increase, eventually, all the stars will burn out. All matter will decay. The universe will reach a state of maximum entropy. Everything will be a uniform, featureless soup of particles at a temperature just barely above absolute zero. No heat differences will exist, which means no work can be done. No complexity, no change, no life. Just a cold, dark, and eternal stillness. It's a chilling thought, isn't it? The final, irreversible victory of chaos. But don't despair just yet. We're talking about timescales so vast they are almost meaningless to us trillions upon trillions of years. For now, entropy is not our enemy, it's the engine of change. It's what allows energy to flow and do work. Without the drive towards higher entropy, the sun wouldn't shine, the wind wouldn't blow, and life as we know it couldn't exist. The very processes that make our world dynamic and interesting are all driven by this fundamental march towards a more probable, more disordered state. So, the next time you see steam rising from a cup of tea, a log burning in a fireplace, or even just the inevitable clutter returning to your desk, you're witnessing the second law of thermodynamics in action. You're seeing the arrow of time pointing forward, driven by the universe's relentless and beautiful embrace of chaos. It's the cosmic rule that explains why things fall apart, but it's also the reason anything happens at all. And that's the profound and powerful story of entropy. It's more than just messiness. It's the law that dictates the flow of time, the existence of life, and the ultimate fate of the entire cosmos. What do you think is the most fascinating aspect of entropy? Let me know down in the comments. Thank you so much for joining me on this journey into the heart of chaos. If you enjoyed unraveling this cosmic mystery, please give this video a thumbs up and consider subscribing for more deep dives into the wonders of science. Hit that notification bell so you won't miss our next adventure. Thanks for watching.